Is it on? Yeah, I think it is. Welcome to Good Old Data. I'm Andrey, and this talk will be about data-oriented programming. I'll tell you what does it mean and what benefit does it provide if applied thoroughly and consistently through to the code base. So first of all, why data? My motivation is that engineers' job is to solve problems. And oftentimes, while doing so, we create more problems that we solve later. And then we create more problems. And oftentimes, these problems have nothing to do with our problem domain. This is something called accidental complexity. These are the problems that were not in the original problem statement. Those are we created ourselves by applying some practices like object orientation, ORMs, functional programming, anything that was not that wasn't in the original problem. I believe that that data orientation helps us to reduce this external complexity and allow us to build simpler and more robust and flexible systems. A little on my background, so you clearly see where I'm coming from. I spent last 14 years at JetBrains building IDEs. After several years of working on IntelliJ, later was a project called UpSource. At about 2015, I've started using Clojure to build a new kind of IDE that would be distributed, collaborative, and cloud-based. That has changed my perspective on software design in many ways, and that has led to Fleet. And later this year, I've applied some of these practices to build Kotlin LSP. So why data? Data is the language of a system. It becomes evident when you start working beyond the boundaries of a single process that you built in Kotlin. It is very rarely that our scope is limited to just a single process and we don't talk to any external services or data sources and persistence, etc. So when we design systems, that's what we usually draw ourselves. Like those are design pictures. Like the software design looks like that. Interestingly enough, if we open our editor, we don't see anything like that. Well, if you do see anything like that opening the editor, you probably shouldn't be here. So somehow language switches. Language in which we reason switches immediately when we start diving into our code. We see way too much code and much less data. These diagrams are usually mostly filled with stuff that have to do with data. Where do we get data? Where does it travel to? And how do we store it? What gets propagated where, when, etc. So oftentimes these things somehow disappears when we start programming in a programming language. Because we have this luxury of shared memory and reliable function calls, we tend to forget what we actually deal with. These things disappear. So I think that two languages, language of a system and language of the programming, should be brought more closely together and should be related in some way. So when we design system, we need to make a lot of decisions. They concern wire protocols, configuration languages, database schemas. We pick storage. We design queues, data pipelines. We introduce caching and all these things. So data is very important for software design. It's all these things revolving around data. The topic is very abstract, and I wanted to cover it with some structure, and so you wouldn't get lost, I'll try to present the plan. First, we'll define what the data is and what it is not. And then we find tools within the language that allow us to implement this concept in Kotlin naturally. And then we see what properties do emerge from the system when you apply these techniques consistently and thoroughly through the code base. So first of all, what is data? Concept of data has existed long before we have started manipulating it with software. And apparently there is a definition for that. These are things known or assumed as facts, making the basis for reasoning and calculation. It's coming from Latin, something given. So this is some information that was given to us from the outside world into our software system so we could process it somehow. Often it's a result of measurement or other ways of inquiry of the outside world. This is rather a philosophical definition, like that predates software. So I'll try to derive 3 fundamental properties from this definition and that are more relatable to software. You might want to derive some other properties from it, but yeah, the slides are immutable, and so is data. If something was given to us as an information about the outside world, the worst we can do is mutate it in place. This mutation does not have effect on the data that it relates to. It doesn't have an effect on the real world. We just mutate it in place. We are forgetting information that was given to us. We are losing stuff. So you cannot assign any meaningful semantics to mutation of data in place. So yeah, there's a recipe to lose your type in a hash map. Data has value semantics. Because it is used for reasoning and calculation, doing logic is impossible without being able to tell data apart. If you cannot say that 2 pieces of data represent the same, that they are the same, it's really hard to build reasoning from there. So if we have something that looks like a pure function that takes the name, returns the capitalized name, and then we ask a question: is it really pure function? If equality returns false, so we're kind of losing the logic here. And third, very important property, and the last one that I derived from it, is that data was given to us, meaning that it was communicated somehow. It was loaded into the computer, so it was serializable when we received it. So this property has to preserve. Being able to serialize data is very important when data travels in time or in space, where we put it on disk. When it's sent, we should be able to send it to somebody else. So, and very important is that this serialization semantics has to be in agreement with the value semantics. That is not trivial. It's very easy to think about serialization as some edge of a system where you can do some normalization or something like that. So here we got some URI, and we basically removed the trailing slash when reading it. That has broken the very basic property that serialization composed with deserialization should give us identity. We should not be able to tell whether data was already in memory or we have performed some kind of a round trip. That should be transparent. So these 2 properties has to be consistent. And that's what I mean when I say data forward the talk. So anything that satisfies the 3, I will call data. So which tool do we have in the language to represent data? We obviously have primitives. Those are just fine. They are immutable. They have value semantics. We can compare integers and strings. They are clearly serializable, and everything is good with them. To build, to compose it, we need aggregates. So we need aggregates when several things are related. I measure temperature and humidity in the same place at the same time, so these two numbers have some relation with one another. So that's when we might want to build an aggregate. When they travel together, we just group data together to send it somewhere else. When we want to build abstraction with data, like we might want to call several things as one and to see it as one. That's where the composition comes from. So we need aggregates. Kotlin, being object-oriented language, gives us objects. So let's look up in Wikipedia, what is object? It's an entity that has state, behavior, and identity. Nothing here resembles this, right? This thing does not have identity, no state, and doesn't say anything about behavior. So we got to find some tool in the language. Previously, there was a talk about immutability coming to Kotlin, and there are immutable value classes are coming to Kotlin. Those should be used. They are amazing. But for now, we had to use data classes with a few constraints. First of all, no vars in data classes. That's a recipe for disaster. That shouldn't be allowed in language. Do not publish mutable collections even if they are presented as immutable lists. Like if you have mutable list, it certainly is a subtype of list, so you can put it in a data class and then continue mutating it. Kotlin will be happy, but you will not be happy. So any fields that you put in this data class has to be data, so it has to preserve all three properties. And that's how we can compose and build a bigger data out of a smaller one. So for serialization, I strongly recommend using Kotlin serialization. It's amazing, and I'll be using it throughout the talk. We might build some collections. Those also could be treated as data if they are effectively mutable and their type parameters are data. So collections have value semantics. You can build your own data. For that, you need to do several things. You define a class, make sure it's immutable, you implement equals and hash code together, and make sure that any operations on this class, returning you a new value of this class, hopefully, preserve the value semantics. So if I applied some operation foo to an object A twice to the same object, I need to get equal results. Yeah, you need to implement serialization, obviously, and make it consistent with value semantics as I described before. You can define abstract data. That's what collections are, by the way. They are list, maps, and sets are interfaces, not classes. Interface being essentially just a group of functions is really hard to assign value semantics to. Because it is computationally impossible to compare two functions, just arbitrary two functions. We need to actively sample and check any possible input of this function to make sure that they are. So in this particular domain, we know that second function accepts only integers up to the length. So we iterate over them and explicitly compare the outcome of this function. Data doesn't have behavior. So we need to be able to associate some the behavior with data. And do not and do it not by implementing some arbitrary interface. That gives us additional benefits, like you should be able to share these data classes throughout the system, between platforms, make it a shared code with server. So let's keep the data, let's keep the code out from these modules that define data. It's a bit tricky to do that polymorphically. Like if we implement interface, we can obviously implement it differently for different types. For sealed hierarchies, that's not a problem. We can just button match. It's easy. For open hierarchies, it becomes a little bit more tricky. We need to create some sort of an external dispatch. So we can assign different behaviors to different types of data, so we can explicitly create ourselves some dispatch value. In this example, editor widget is a widget, but it does not implement any interface. Instead, we create a special dispatch value and assign the behavior to this dispatch value. So we can put it in some hash map, like register UI puts the function into a hash map. We create this dispatch value to be also data. That is very important. Do not use k-class for dispatch, because k-class is not data. This way we can say the polymorphic pair, like widget, built from widget type and the T itself, is also data. And also like list of all supported widget types becomes data. So it propagates further and it's just good. So we work hard. We've broken a little bit our habits. So what properties do we have from that? So let's put data into context of computation. What happens with our systems when we compute with data? Meaning that we can express the computation itself as data that returns data and and accepts data. First of all, we can leverage data locality. That's very simple. That's what we do all day working with databases. We can apply it further, not only to databases, that's the same trick. You can serialize the computation needed. If it returns data, you can always move it somewhere else. So it could be closer to data, or it could be more secure, or you don't want to expose your LLM queries, you're free to move the computation to your private network, for example. There are less trivial examples of that. Not going to talk too much about it, but go check it out. It's called Rama. That's a framework for building backends on JVM. They take it to extreme. They say that they combine storage and computation in one node. They don't use databases, so the persistent storage is the node itself. Everything is sharded, and data is partitioned. So their computation can be arbitrarily scaled through many nodes. And they have very nice example. They built a Mastodon server, which is which scales to the Twitter scale. And go check it out. It's really cool. They define stuff like depots, p-states, source outs, and they do batching, aggregation, and all these things. And I think they miss Kotlin DSL for that. So that's their Java examples. It's really cool. When computing with data, we can leverage computation avoidance. Any source of computation avoidance relies on data properties. We don't think about it a lot, but it doesn't work without any of them. Like, it has to be value semantics so that we can tell that some inputs did not change. This question of equality appears there. And if data is mutable, we cannot. And if data is serializable, we can move the cache out of our process, put it off heap, or share it with other nodes, and do beautiful things with it. So frameworks like Compose actually rely on value semantics and all these properties. You can, Compose will skip computation of completion pop-up if the completion data in the text editor data has not changed. That happens because it doesn't use hash maps. It uses slot table to store the previous value, but it relies on ability to tell information apart. So it is important. If we add serialization to compose, we can create beasts like that. That's server-side rendering with compose. It could work like that. We can define some data class and share it between client and server, define the dispatch value as we did before, and run 2 separate compose runtimes. One will be controlling another. On a server, compose will yield the client component that will serialize its parameters, get to the client. Client will register the random function for that, and it will create its own state. So these kind of things become possible, and I think they have their application in some enterprise apps or something. My favorite part, like that was just for starters. Like if you compute with data, you get all this stuff. My favorite part is what happens when you represent state with data. Well, first, let's go to the dictionary. What is state? It's a particular condition that someone or something is in at a specific time. And the system is described as stateful if it is designed to remember preceding events or user interaction. That remembered information is called the state of the system. I kind of forgot to mention that in previous code snippets that I was showing, I used the pink highlighting to denote data. Here I will introduce another color to denote identity. So here this someone or something that is in condition is the identity. And the condition itself is just the state. It's data. So the concept of state is closely related to things like time, events, and being able to remember, and the identity. So the identity is just the ability to point at something and say that this particular entity has changed the state. Identity is associated with state in some arbitrary way. There are many ways to do that, but that's the idea. That's something that remains stable, even though your friend has changed email. It is still the same person, probably. So here it could be clearly seen, like, what do I mean by identity? Like, user ID is identity, user state is the state. And they are connected in some way, external to this code. Somewhere else there is an association between users and their state. And obviously don't use reference to represent it. Don't use Kotlin references as identities, because it doesn't work, because it makes stuff mutable. And yeah, we do that all the time when we work with databases. We have IDs everywhere, and I argue that we should be doing that anywhere else, because there is no reason not to. So how do we perform the transition? What does it mean to change the state? What's the process of remembering? Remembering can be seen as a pure function that takes the event and the state, producing the new state. And then somehow we need to update the association between the identity and the state. Identity could be an atomic reference, it could be state flow, it could be a hash map, it could be anything. So that's not important here. The important part is that we do not forget the previous state, we just swap a single atomic reference or something like that. That might seem like a bit of a bit inefficient. But the thing is that everything that we described before is actually trees. Data classes with data fields are trees, and so are persistent collections, which you can find in Kotlin X collections mutable. They are amazing. They are very high branching factor trees, so you never do more than 6 lookups, 6 pointer chases when you look up stuff in there, unless you have collisions, of course. And they share a lot of structure with the previous version when you create the next one, so that your overhead in terms of copying isn't that big. You just copy 6 nodes at most in a really populated collection. So use them, they are very good. And the important part is that this technique could be used far beyond just implementing collections. Git is made exactly this way. You can do that on disk. You can do that in key value stores by using hash addressable values or do stuff like that. So state has something to do with time. How do we build time from that? Easy, we can just we apply events to the previous state to produce the next one, and we need some coordination mechanism to update the pointer and to update this association with the new state. It is important that these readers on a diagram, they do not interfere with the process of creating the next state, and the process itself is not stopped when readers comes in. So that's very similar to the perception in real world. When we see the movie, we don't need to press pause on every frame just to see it. It can go. We probably missed something, but that's okay for us. We can still deduce what's happening on the screen, right? So state done right never requires readers to coordinate in any way. Let's put that in code already. This is a little fleet that I managed to put in one slide. Pink here is the state and data, and the greenish ones are identities. So we put the entire state of our editor into a single data class, which contains a persistent map from URI to the documents. Document has the text, which is a persistent data structure, holding the string. It's very similar to string, but it's more efficient for updates. And we have everything we need here. We have perception. We have a composable function that displays the UI. That is somebody who lags behind. If we update the state and frame is being currently composed, we don't need to interfere with them, and they will eventually catch up with us. So this is our reader. Our process is when we dispatch an event. That updates the state. So that is independent from composition logic and happens concurrently. It is important that we make events to be data too, because this way we can capture the real intent of the user into this thing and apply it to different kinds of state, because it is important that there is an asynchrony here. Because reader is behind, it might decide to issue a state transition. And the identity itself might be in a completely new state that we haven't seen. So this application of events should take care of that. So if we type a letter, we can apply the typing to any state. And by the way, there is a bug here, right? Because it has captured the offset might not be there. So we need to be very very careful here with asynchronicity. We did that. What did we get for it? First of all, we can jump back in time. We can record all the states in some array and just swap the pointer and see the past value in our UI displayed. Everything's good. We can record events to replay them later. We can replay them on any other state. We can roll back and replay some other events. And these are the stuff that's usually hard to get from the UI applications. We can replicate state. We can maintain two identities and apply the same events to them so that they will be consistent. We can store this event on disk and replay them later together with a snapshot. Snapshot is data, events are data, so we can just store them incrementally and get very good things from it. We can parallelize any computation in the state because perception does not require coordination. We don't need to stop the world to perform heavy diff computation on text, for example. And my favorite part is that we get optimistic updates. Imagine we have two different computers that started with the same state. And they both independently and concurrently experience two different events. The first one experienced event 1, the second event 2, they don't know about each other at all. And then they exchange events with one another in some way. We may take a decision who comes first. For example, we could sort UIDs. That would do. And then the second one got lucky, and the first one needs to discard their event 1, apply event 2 first, come up with a state 2, apply event 1 to it, and get exactly the same state. That's the key to collaboration. I mean, real-time collaboration like in Figma or in Fleet. In Fleet, it works this way. So we don't really need any operation transformation. We don't need CRDTs and all this complex stuff. We can just apply functional programming. So we can actually, the thing with the correctness that we can apply events in different order actually is coming from this asynchronicity that I described before. The fact that you are lagging behind makes your events be applicable to the future. And if it's applicable to the future, you haven't seen this event that has came before you. And so we can use exactly the same property here and just reorder them, and that will be correct. So we got optimistic updates, real-time collaboration. We got observability of our state. For that, I mean, like in object orientation, we used to be using listeners for that. Listeners had their own drawbacks. Here we can model the observation as a flow that contains either a snapshot or an incremental change. We are free to subscribe to this log of events at any time. We can go away. We could survive the back pressure policy. Like if somebody is taking too long to consume these events, they might lose it and get the new snapshot. And we can, because everything is serializable, we can observe the state of a system from like remotely. We can do that from afar. And yeah, those are kind of benefits that you get from modeling state as data. Another cool place where we could squeeze data in is effects. Effect systems deserve their own talk. I'm not here to talk too much about effects as an idea, but the idea is that instead of doing side effects right in our code, we can extract them into some data and apply them indirectly through some effect handler. So if we are, for example, to implement something like a coding agent, that would, like a very simplistic one, it runs a while loop and tries to fix tests. We could call to LLM, get some edit, apply the edit, and then we run tests, and if it succeeds, we commit. Like, it's not that simple, but in our example, that is very useful. So if we model effects as data, we can record events and their results so that we could stop our agent and run it later, perhaps even on a different computer. We can act at a distance. This thing doesn't say on which computer do we perform the effect. That also allows us to test our code much easier by just recording events instead of doing something like mocks and whatnot. We can just record them in JSON file and use that as test. So it's time to wrap up. These are my yeah, what did we learn? That why do they appear that way? Okay. I'm sorry. That did not mean to be like that. Come on. Come in. Yeah, this way. This is the our abstraction tool set. Whenever we build whenever we need an abstraction, first we need to consider data as a tool, and only if that doesn't work completely, we can use pure functions. If that doesn't work, we need some heavy polymorphism. We want to use immutable interfaces, and if that doesn't work, we can use suspending effective functions. So those should be applied in this order to give us the most power. Consider making everything in your system data, events, state, effects, maybe other things, configuration. When we build in Kotlin, we love building DSLs. It is much better if DSL is building data instead of doing immediate effects, because code always loses to data in ability to reason about it and do different things to it. It's hard to analyze code. It's easy to analyze data. So keep code separate from data. It enables data reuse, and do not confuse identity and value. So our knowledge about things are not that things themselves. That's the big idea that took me a while to realize, that we should not create these ambassadors from the real world, call them objects, and do simulation, because those are rarely good choice for your systems. If you want to create some class like user in a program, consider just calling it user data, and that will help a lot to see things differently. So that's it. I finished earlier. Yeah, maybe let's discuss something.